Let's get started. This is our research jam number 11. I think it's the last one of this year. I didn't calculate what's the next one. Maybe either December or probably early next year. So great to see you guys here. Today we have 3 speakers. So before we get started, I have to show you my dog basking in the sun.
So nice.
I envy his life.
Uh,
Right. Then let's get started. We'll go with the order of Jacob, Prakar, and Ali. So let's get started with Jacob.
Good morning. I want to show you a framework that I'm in the progress of developing. I hope will help all developers or help machine learning to be more accessible to developers in general. So this is called TensorCode. And simply, TensorCode is a framework that allows you to integrate your tensors with classical code. A lot of times in programming, we spend a lot of our code on encoding and decoding the inputs and the outputs, and then writing the algorithm in between. And TensorCode is going to make hopefully all of this differentiable. So it will provide convenience functions to encode and decode arbitrary Python objects. And that will be useful for developing and evolving multimodal models. It will integrate runtime code generation systems like Copilot with the actual interpreter. So you can I want TensorCode to make it possible for you to execute strategies that are built on the fly. And more generally, I want TensorCode to be the framework that helps people get into differentiable programming. So if they want to have a little bit of magic in their program, they don't know what variables to query and what values they should be looking for, but they know that there is a certain binary decision to make at some point in the program, they can just call this machine learning oracle, and over time, the program can learn the right decisions to make. And I hope that all of these convenience resources, these abstractions, and tools that the TensorCode framework provides are the foundation for the next generation of cognitive architectures. So I want to start with an example. Imagine you have an agent, it takes in the screen bitmap, the energy that it has, and it produces an action like left-right motion. Now this agent, over time, we may add additional input modalities to it. So we might add output modalities like running, jumping, 3D motion, and then we also want it to be able to take in an English language command. The environment may change as well. The environment provides depth vision and other hand-engineered features. And so as these modalities change, the agent needs to evolve along with its environment. Right now, a lot of the code that we use is very low level. So we may have the vision gets processed by a VIT, and the text, the command by a GPT, and concatenate that all and build a latent space and actually make the action and so forth. You can see that this is a very detailed, very not super low level, but this still requires paying more attention to the inputs and outputs than may be necessary for an agent that is able to adapt to arbitrary modalities. And so TensorCode provides 2 convenience functions for this, encode and decode. And with the encode function, you just pass it a pure Python object, something that has a dictionary attribute. It reads the keys and reads the values and then performs attention on that object recursively to build a latent representation. And then the TensorCode decode function, it looks at the target shape of the object that it wants to create and initializes the fields appropriately with an input latent vector. So all this 8 lines of complex code, TensorCode may make it possible for developers to simplify down to just 3 lines of code. And then the actual action and observation shape classes themselves, right now they're shaped like this. Let's say we wanted to add additional observations, we would just be changing the class. We wouldn't be changing the algorithm. And then if we wanted to add additional actions, likewise, we would just be changing the class and not the algorithm. And conveniently, in Python and in many other languages, there are software engineering patterns like define a custom type. So right now in machine learning, your environments often It's a handwritten, unspecified, informally specified rule that if the action is between this value and this value, this means do that. And if it's between value B and value C, then it means do this action. So we can make this explicit by using constants whenever we define the structure of the action. And this will make the whole code base, I hope, able to evolve better through time and more efficiently with multiple developers. So this is just an example of how TensorCode is useful for encoding and decoding arbitrary objects. Under the hood, this algorithm starts by generating, let me go back one. Okay, so under the hood, the algorithm starts by looking at the structure of the object that it's querying. And in this case, it's querying an observation. This observation has 3 attributes: vision, text, and energy. And then it converts that into a dictionary. All pure Python objects have a dictionary attribute. It converts each of those sub elements recursively into tensors, and the tensors are initialized. They can be overridden, or they have a default way of converting them into tensor form. And then the query, which starts by the name of the type, initializes the query for the transformer. And then the transformer performs recursive attention over the keys. And then based on the matching key, the highest matching key, it queries the values in that key. And I think that this is a way, we saw the perceiver IO and related models by DeepMind, how they were able to scale linearly with the size of input length. I think this is a way to scale linearly with the shape of input size for arbitrary shapes, not just for text, not just for video, but for any kind of contrived structure that we come across in software engineering.
Hey, Jacob, you mentioned the model, takes the highest attention and then looks at that tensor. Is it actually a soft attention across all the tensors though, or is it really a hard attention?
So this is, let me emphasize, this is a plan. It's not implemented yet,
Okay.
but I'm planning on making it perform deterministic hard attention. And the reason why is it's going to perform recursive attention anyway. So if it needs to get multiple queries, it can just do that incrementally. And objects, they get very big easily. And I mean, not all objects, but I can't assume how big an object will be. I want this to just be able to, on the fly, determine what it needs to be looking at and then prioritize its focus. And if it needs to look at other keys, it can look them up later.
You could try, you could use deterministic hard attention. You could also use deterministic soft attention, right? But yeah, like you said, if the objects are getting really large and you want to save some compute.
Yeah.
Yeah.
And another thing is that I want to have it automatically break up images into patches and sequences into patches. So like on the top of the slide, this text is just a regular text encoding tokens, but down the bottom, it's broken the text encoding into a separate list of keys and list of values. And so it's only going to query one token at a time, similar to the perceiver network. But this is again, this is super duper in the planning stage. So I do like that idea of forming soft attention, and I'll experiment with different approaches to attention mechanism.
To keep it all in easy to use Python, you could allow users to give like hints for fields. Like when there's the field vision colon and an image, they could provide a hint for like, this is how you might chop this up, or how you could chop this up into patches. And then your model could choose to use that hint or not.
That's a really nice idea. I think I'll implement that because, yeah, that is important. That's probably going to be more prompt engineering in that area as well. So some other functionality that I want to implement in TensorCode is runtime code generation. And many of us use Copilot, I'm assuming, or we've seen it. A lot of times, the code that you want to generate, you can generate at develop time, no problem. And it's just convenient to be able to have the code generated by someone else and not by yourself. Other times, even if you were using Copilot, you wouldn't know what code to write until you were in the runtime and with the current state of the program as it is. For example, you need to construct an execution strategy for an SQL query, or you need an agent to give you an explainable list of actions that it's going to execute before it performs the execution. Those are use cases for runtime code generation. And this is an example of how the code might look. You would ask it to select an object based off of a natural language query, and then it would use the encode function to encode the objects, and then select the highest performing, most diverse model. Or you could have it create an object similar to decode, but you also provide context information for it to use when creating the object. And I also want to make it possible to structure the creation with design patterns. So TensorCode is going to have a library of design patterns that almost make it possible for just non-machine learning enhanced code generation, but that will help structure the code that it generates in a way that's very explainable and easy for other developers to contribute with. And then finally, differentiable programming. I think that this is a way that a lot of the models we make now, they're just like a DFA. They just go from layer 1 to layers 3, 4, 5 to layer 6, and then to the output head. But there's no decision making in that kind of a neural network. And so with differentiable programming, the information in a neural network, we may end up seeing neural networks that are extremely recursive, and not just recursive in a simple loop for n times and then output, and not just a decision transformer like, I'm sorry, not decision, a universal transformer like let's keep on recursing until a certain criteria has met and then we'll output. But what I mean is, very complex algorithms that are differentiable. So we could decide we're going to do X and then we're going to do Y. And if this case is met, then we'll go back to X. But if that case is met, we'll go to Y and go to Z and then meet the output. And there may be a lot of unexplored complexity and scaling in the direction of algorithmic complexity. That's what I would like to implement in TensorCode.
And so to make sure we have time for everyone, is it possible to wrap up in like 1 to 2 minutes?
Yeah. Okay. So yeah, and the big picture here is cognitive architectures, really complex machine learning systems. TensorCode is going to, I hope, be useful for building these large systems. And so this kind of complex graph, it might be able to fit into a single Python function like we see here. So that's a high-level plan for what I am developing with TensorCode. And thank you for your attention in this presentation.
So afterward, there will be 3 channels in Discord, so people can hop over there and ask questions of Jacob and the other presenters. I think we have a couple minutes for maybe 1 or 2 questions. If anyone has
I see one. I see unapplied. Oh, thank you. Any other questions?
One question I have is, what do you think will be the hardest part of implementing all of this and getting it all to work?
Oh, I think it's easy. Well, no, I think it's straightforward to write the code that will perform recursive attention, and that will make the code objects be queried and selected and decoded in runtime. I think the hard part is developing a methodology for debugging the semantic problems that you could have with TensorCode models, because these algorithms are really algorithms. Every algorithm has a different intuition for how things work, and human intuition only covers a very small set of algorithms. And so I think that that's going to be the hardest part, and that's something that I can't generalize to right now.
Yeah. Any other questions for Jacob?
My question would be, once you code a prototype of this, you probably need to provide an intuitive example of how to use this. So what kind of example are you thinking that has all these kind of inputs, and you have to make a decision on top of all these image, video, text, and inputs?
Yeah, I think I can't stop thinking about cognitive architecture. That's a bias I have, but that's what I want to develop, is a human level cognitive architecture that will interact with the computer, make keystrokes and mouse actions like Adept AI has made, but they use it. I don't know how they do it, but they use it sounds like a simpler transformer to do everything. But I think that the transformers today, a lot of their activations that from this one paper I read, that a lot of the activations are very insignificant, and there's only a few significant activations in large transformers. And so I think that there's a middle ground between classical machine learning and classical programming, and that's what I want TensorCode to fill. And then the very large models that right now they take hundreds of gigabytes of memory, maybe they can be compressed into a very small narrow symbolic program that can run on a laptop. And that's what I would like to see with TensorCode.
If you haven't registered tensorcode.com or .ai, maybe you should do it now.
Okay, yeah, I'll do that.
Video.
Thank you for.
But yeah, thank you. We can move on to Prakar. You're here.
Hi everyone. I'll present an update of sorts for what I did present in the last research jam. So let's just dive into it. So I'll quickly go through some brief background of why I wanted to do this. So prompt engineering, as I think everyone is aware, is quite powerful, but not naive. It's quite hard, and we know that prompt engineering is quite sensitive to the prompt, whether it's the template or the examples chosen for context, or even the order of these examples. But we don't talk about the sensitivity of prompt engineering to changing model behavior. Now, forgetting in deep learning is actually quite well known that deep learning models tend to change their behavior a lot even after so-called training loss convergence. The problem that I see right now is that the whole NLP community kind of just works with a few pre-trained checkpoint set, and that's what is driving the whole in-context learning field. And this doesn't really account for a randomness in model training and behaviors like forgetting. So that's what I wanted to explore. So let me start with the experiment setup. Just go through all the dry details first. So I'm working with a Roberta large model, which is pre-trained for 2 million steps. And maybe I can, okay. Yeah, so I'm going to talk about two sets of experiments. The first is I take the pre-trained model and I train it for another 1,000 steps with the simple MLM objective. This is to kind of simulate the model behavior during training. And secondly, I fine-tune the model on with PET. So PET is essentially just using the prompt template to fine-tune the model. And then once the model is fine-tuned, I'll continue the training with MLM or try PET with a different label word to see what happens if I force explicit distribution shift. How does the model change its behavior? So
just to make sure we all understand, so MLM, you're saying this is the masking objective, so predicting masked words?
Yes, sorry, I should. Yeah, the MLM is masked language modeling objective. So essentially, it's masking randomly 15% of the words, and then you're trying to predict those words in the sentence here.
Okay, and what's PET?
PET is like it's maybe I can. Okay, so it's kind of like this. So let's say you have a sentence. You add the template, the prompt template that you want to use during test time. And now the task is just to predict the mask correctly to whatever label words you have chosen. So you are directly fine-tuning for the prompt that you want to check during test time. I hope that makes sense.
It's MLM, but with the prompt in as
Yes,
context?
yes. So it's not random masking, it's masking exactly one word, which is the label that we want during test time.
Okay, I see. Thanks.
Right. So yeah, so we do a PET for some label words, and then we'll try to change the training objective and see how the model changes its behavior. So the testing setup is quite straightforward. It's a k-short learning, k-short classification. So you take k examples from each class. K is 8 here. You shuffle the examples, then you fit them into a prompt. So for example, this would be the sentence, it was the label word, the sentence, it was then label word, and so on and so forth. And then you have a test sentence, and then you add the same template and you check the logit values for the mask. You compare good versus bad or whatever label words you have chosen. So prompts in general are quite sensitive. I'll first start by comparing the sensitivity of prompts to the training samples that are actually chosen in context. So we start by a simple setup where I randomly sample the k-short that I discussed earlier. And based on that sampling, we can see a huge variance in performance from like almost random guessing to 80% accuracy on SST2 with good, bad label words. Now, what I do is I start with the best set of so-called prompts and worst set of prompts, and then I reorder them. This is another thing that is well known in literature, that if you just reorder the prompts, that also is the prompt performance is very sensitive to that. So if you just simply reorder the so-called best or worst orderings, sets of prompts, you still get huge variance in performance. But till now, this is just about changing the prompt. Now, let's say we have fixed the prompt. We had a prompt that was the best order, the best set, or the worst order, the worst set. But now we are comparing how the model behaves during training, which was the MLM objective that I just mentioned. So we can see that the variance caused by the models changing behavior, even though we have a fixed prompt, is almost as large as some other aspects that are actually known in literature. So it is quite important that we, when we talk about that, say one prompt is better than another, then we can't really have a discussion on a single checkpoint. So maybe let me jump to this results. This is a bit interesting. So the setup is there are 6 different types of label words. So each of them is a different prompt, and this prompt performance is measured through the 1,000 steps that I just mentioned for MLM training. As you can see, none of them are really very stable, except maybe say cat, dog, and dog, cat, but they are not real. They are basically random guess. They are nonsensical words. They don't really represent positive or negative labels. So
how big is this test set?
SST2, it's 1,000 examples more or less.
Okay.
Yeah. So there's a huge variance in the performance across during training based on whatever label word you have. Like just for example, the great terrible. So the 0 here is the Roberta large pre-trained model. So if I had just taken that checkpoint, the great terrible performance is really bad. But there are points in the middle where it actually performs decently well. Similarly, the irresistible pathetic version performs decent but drops significantly. So the point here is just to highlight that comparisons that are present in literature, they are usually done on a single checkpoint, which is clearly not a good way to go forward. And maybe I'll skip this actually. Okay. So another thing that I want to discuss is catastrophic forgetting, which is you train a model on certain distribution, and then you change the distribution of training, and you see how the model behaves during that change. So we start with the Roberta large. We train it with the pet setup for 1,000 steps. So we want the model to uh, think of to predict cat when it wants to predict the positive label and dog when it wants to predict the negative label. We train the model for 1,000 steps, and then we change the setup of training. I'll describe later what the change is. They will play with multiple things. And the general expectation obviously is that the performance will go down, but how quickly does the performance go down is more interesting. So we played with 3 different setups. We did pet followed by MLM, pet followed by a different pet for different label words, and pet followed by the same label words but flipped. And the if you look at the performance drop, let's look from right to left. So the rightmost performance drop is actually expected because we have simply flipped the labels. So essentially, I'm expecting the model to predict. I have trained the model to consider dog as a positive label, but then I'm expecting it to predict it as a negative label. So obviously, I'm going to see a huge drop in performance. It's the central and the left graph that are actually quite interesting. So what you'll notice is that even though there is a slower trend of drop for MLM and a more immediate drop for PET, they both seem to recover their performances. This is surprising because just the cat dog labels were not performing very well when we were just training it on normal model. So there is this residual learning that it got when it trained on PET, but uh, it lost it and it gained it again. So let's start with this example. So at the point 0, the model was trained specifically for cat dog labels, so it performs really well. As soon as it's fine-tuned for tiger and wolf labels, it suddenly sees a drop in performance, which is expected. It's this increase that is surprising because it seems like the model later suddenly regains the ability to do predictions with the cat and dog labels. So this graph is actually the mean and median and range and so on. So I also have separate runs for a few prompts, and they all replicate similar behavior, which is, for example, here the models had great performances. As soon as they were fine-tuned on the tiger wolf set, they suddenly had a drop, which is understandable. But then there are points in the middle when they seem to go up again. So basically the idea here is, number one, in context learning is highly unstable during training. Whenever we are doing any form of comparison or any form of trends that are extracted from language models or claims that are made, I think it is very important to understand that they do not generalize well, not just across architecture or prompts or whatever, but just even across that same model during training. And secondly, even though in context learning does roughly follow the trends of catastrophic forgetting that are actually expected under distribution shift, there are significant outliers of the learning re-emerging uh, after like going through a dip, which is, I'm not sure how to explain it, but I think this is something that definitely needs to be looked into. That I'm not, they are like all tangents in my mind, but these are the things that I want to explore further. Obviously, I want to diversify to more data sets and models. I want to isolate and try and study the forgetting behavior and see these outliers which re-emerged, what exactly is happening there. There are a lot of claims that exist, like language models can do self-debiasing, they don't handle negation well, they can simply repeat private information or memorized information. Maybe they can repeat memorized information, but the fact that the model changes so much can help us understand how to make certain information more private than another, and so on. Similarly, there is this issue that exists in language models and NLP in general. When the models get this big, it's very difficult to account for the randomness in training. Like I can't simply run 50, I don't know, Bloom models for training. That's not feasible. So I think the fact that there is variance during training of a model, and this whole tale of literature that exists, that there are no isolated local minimas, like the loss landscape is connected between different minimas. I believe this can help us use the training instability as a proxy to understand what the model would behave like if we would have trained 50, 100 different models. So that is, I think, promising direction that I can look into. Sorry. Yeah, that's that's all.
Nice. That's an interesting phenomenon you've observed. We're running a little short on time, so I think we should defer questions to Discord. If you have any questions for Prakar, after the next presentation, after Ali's presentation, we'll all head over to Discord and we can ask Prakar some questions.
Cool.
And let's move forward to Ali. You want to share your screen?
Hi everyone.
Hey, Ali.
Thank you for the opportunity. I am actually not a machine learning researcher. I'm trying to get into machine learning research, and I want to present this idea I have. The overall idea is to get to a rotation invariant representations of images, and I'm trying to do this by modifying the SimCLR algorithm. So to get an overview of the SimCLR algorithm, the SimCLR is a method of unsupervised learning, and it tries to achieve a good representation, which is invariant to transformations like crop and changing in color. And the loss function is designed to make representations of transformations of the same image closer to each other and of different images farther. So the algorithm has 4 components: the transformation, which we discussed, the encoder, which is a usual ResNet, and the projection layer, which is a single fully connected layer, and at the last, the contrastive loss function. So the overall algorithm tries to update the F and G to optimize contrastive loss, and at the end returns the F. And you can see an animation of the loss function here. So my main idea is to add 3D rotations as a transformation in the SimCLR algorithm, and I hope that this will enhance the 3D understanding of the algorithm and so increase its performance. So I am trying to use the Vista 2017 dataset, which is a unsupervised domain adaptation task that you have train and validation data sets of different distributions. You have labels on train, and you try to predict labels on the validation dataset. The train dataset consists of 3D models and the renderings with different camera angles and lights, and the validation data sets consists of real images in the same categories. So I have trained unsupervised on a combined data set of train and validation, and removed the MLP, attached a linear layer, trained on almost 10% of training labels and evaluated the accuracy on the validation labels. So the loss function was decreasing, so the model was working, but the adaptation accuracy, I'm not sure if that's the correct name, wasn't improving, and actually it was worsening. So I have some ideas which I like to get your kind feedbacks on if you have the time. And my ideas is to first to change the loss function and create it and make it more sensitive to the categories in the trained data set. And I also think that reducing the dimension of encoder by not actually throwing away the MLP and reducing the dimension of the representation to something like 10 could improve the results. And also, I like to add the pre-trained SimCLR ResNet instead of the usual ResNet which I'm currently using. Here I have written the loss function which I'm trying to implement. I try to penalize the similarity of images in different categories more than the images in the same categories, and do not touch the penalties on the images which I don't have a label on. So I would like to get your feedbacks on this, and I'm on my own on this thing, and I would appreciate any mentoring and computation support if I could have. Thank you.
Nice. Yeah, it's a great start on this path. Can you go back to the plot of the training loss?
Yes.
Yeah.
So
I don't have the SimCLR loss memorized, but what training loss would we expect if you had not trained anything at all? So like step 0, if you initialize the model, just a random model, what loss should you get?
I don't actually know that, but that's a very good point. Thank you for
well, so I guess your very first point here, 6.146 is probably either with 0 steps of training, or you're showing epochs. Your training is it 6,000 epochs of training?
No, it's steps. I trained for 20 epochs.
I see. Okay, so your very first point is either epoch 0, meaning no updates have been applied, or maybe epoch 1 after a whole epoch of updates has been applied. Do you know which it is?
It's after the first epoch. I don't have the plus before the epoch.
Okay.
It's actually on each step. If I'm not wrong, yes, it's computable on each batch size actually, I think.
Okay, that makes sense. So SimCLR, are you using its cross entropy over the batch, right?
Right.
How big is the batch?
256 currently I'm using.
Okay. All right. Well, I'm not exactly sure what loss we would expect if everything was completely random, but it seems like the model is just not really learning at all, right? So you're going from 6.146 to 6.14. So that's hardly any motion. How much wall clock time does this take?
Wall clock, you mean how much time did it take to train the 20 epochs?
Yeah.
Right, it took around 3 hours, if I'm not wrong.
Okay. So if it took much less than 2 hours, I would say just train much longer. But if you're already taking several hours and it's hardly making any progress, then I think you just need to debug the training process. Like it's not really making the progress you would hope. So you could try changing the learning rate. Maybe you need a 100 times larger learning rate or something. Some of these models with quite different losses than typical classifier cross entropy, the learning rates we're used to seeing for other models maybe don't apply, and you need to use much larger learning rates. So I would do a quick study, like 10x learning rate, 100x learning rate, 1000x learning rate, maybe 0.1, 0.01 if you want. Just explore in log space, like a very wide range of learning rates, and see which produces the best model after, say, like 20 minutes of training. And based on that, you can kind of fine tune the learning rate. There might be other parameters, like you mentioned, tweaking the loss a bit to change the weightings of different factors. But more or less, just looking at this plot, I would say the problem is your model isn't really learning much at all.
Thank you very much. Thank you very much for the feedback. I really appreciate it.
Also, I would, yeah, never mind. On compute though, probably we could get you some compute. I think,
Yep.
Roseanne, we have extra right now, right?
Yeah, and Daniel here who can
Oh, yeah.
help set up. Which code base are you based this on? Is it the standard SimClear code base released?
No, I started from the PyTorch Lightning implementation.
Okay. Might be worth it to just run like a baseline method from that code base itself to see if it can reproduce the simplest example, just to debug from the very beginning.
Right.
It's a really
Without
good idea.
using your data set.
Yeah, I would definitely try to run their code base on a data set where you know what you should expect, like normal images train set and normal images validation set. Your 3D rotation example is, it might be extra hard in some different direction. And you want to know what's the problem with your data set versus the model or the training regime or the hyperparameters.
Thank you very much. So I guess it haven't trained at all. So I should try to fix that first.
Yeah.
Many thanks for your feedback.
And then, so how big are these? What kind of ResNet is it?
It's the ResNet 50.
Okay, so you're getting through 6,000 training steps. So that's 6,000 training steps on a batch size of 256.
Right.
Right. 6,000 training steps times batch size 256. Well, 6,000 training steps in, and you said 2 hours.
Yes.
So that's more or less one batch per second.
Yes, it was.
Are you using a GPU or not?
Yes, I was using a Tesla T4, I guess. I'm not sure.
Okay.
It was
So, I mean, I think that's not insanely slow. It feels a bit slow, but it's not crazy slow. You could look at how much time is spent in the model, forward pass, backward pass, update, versus in all the pre-processing. So maybe rendering the images. Are you pre-rendering the whole data set, or is it rendered live?
It was pre-rendered, and it's about 5% the pre-processing relative to the actual forward and backward. Right.
Okay. As long as you're keeping tabs on all that and making sure you're using the GPU well, then maybe that seems reasonable. Maybe with some of the compute help, if you used Colab, maybe the GPUs would be faster.
Thank you very much.
Does anyone else on the call have experience with SimCLR? If so, any advice?
I think the original SimCLR paper, they trained on ImageNet, but it took a ton of compute. So I would suggest getting a very simple model, working on find a really small model that's working and try to re-implement it. Similar to what Roseanne said, because the SimCLR paper, you got to get the training done, but then the augmentations mattered a lot in that paper. I think they did a augmentation ablation study, and they said color jitter and crop were very important. So that just means it's going to be a really large search space. So I think you gotta get a working simple baseline you understand, and then when you got that going, then move on to your 3D idea, which I think is really cool actually. But then you're gonna have to figure out what augmentations you want there or what are needed there, and that depends on your data set.
So I might need to change the augmentations for the 3D idea.
That's further down the line, but I think you got to get a really simple working example of this technique on a you need to replicate someone's results maybe on a smaller scale if possible, just to reduce the compute time.
Yeah, I think
Right,
that's
right,
good.
yes.
That's really good advice. I would start with a standard data set where you can find someone else's SimCLR results for train set images with normal augmentations, test set images or validation set images, normal augmentation or no augmentations, I guess. So step one, just reproduce standard SimCLR on a standard image data set where the augmentations are known to be working. And then you could go to your data set with the planes and maybe take your validation set, which is non-rendered images, split that into a new training set and smaller validation set, and just train on image augmentations for that training set. And then try your 3D idea.
Right, many thanks. Many thanks for the feedbacks. I think I'm a much better place now, and I will start to implement the standard SimCLR first. Many thanks.
Any other comments, or we can switch to Discord? Maybe let's give one more thanks to all the speakers.
For those who can stay, we can move on to Discord. But if you have work to do, we understand. So research jam presentations are either getting your project started or looking back on how much progress you've made since the last one. And we can also use this chance to gather mentorship and compute support. So any presenters are qualified to get compute support from us. Just email compute@mlcollective.org. We'll get it handled.
All right, see you guys in Discord.
See you there.